Hello friends, welcome to the course Exploratory Data Analysis for Data Science with R software. You can recall that in the last couple of lectures we have covered the topics of graphical presentation, and we have learned that how different types of graphics can be made constructed in the R software using different types of packages. Now, from this lecture we are going to begin about a new topic, which is about a new aspect of the data science. This is about central tendency of data. You see, whenever a process is happening, we want to understand the different aspects of that process. Now, we can conceptually understand what we want to know, but these aspects have to be translated into a mathematical setup in a statistical framework. And beside those things, one thing you always have to keep in mind, that whenever we are dealing with statistics or data science, the data is going to have some variations, some variability. Well, how to measure this variability, that is a different concept that we will discuss later. But our main objective in statistics is that we have to develop the statistical tool in such a way which can measure the aspect with minimum variation, with minimum random variation. And with this objective only, we try to create different types of statistical tool to measure different types of aspects of the data. And among those aspects, one of the very important aspect is the mean values. We want to measure the average values of the data, or we want to study the central tendency of the data. We want to know around which value the data is concentrated. Suppose we want to know the age of the students in a class. Now, if suppose there are 100 students, somebody says my age is 20 years, someone says 19 years, 21 years, 23 years, 18 years, 19 years, 20 years, and so on. What will you understand from this data? These are the individual values. And if you really want to understand what the data is trying to inform us, then one simple objective is this, or one simple solution is this, that we want to see around which value the data is concentrated. So, with this objective, we can study the behavior of the data, or to concentrate around some value. And whatsoever is this value, that will give us an idea about the central tendency or the average value of the data. Now, in statistics, there are different types of measures of central tendency: arithmetic mean, geometric mean, harmonic mean, median, etc. And these measures are used under a variety of situations to capture the behavior of the data in the true sense or correctly. So, now our objective in this lecture and in the forthcoming lecture is that we want to understand what are these different measures of central tendency, how they are measuring the mean value, what is the interpretation, and under what type of situations they can be used. Then, how these things can be computed in the R software. When we are dealing with the R software, then there can be two situations. Then all the data is available to us, or some data is missing. So, how to operate these statistical measures under these two conditions is another point which we would like to study. When we are talking about the data can come from either continuous variable, discrete variable, or categorical variable, and so on. So, these measures, how they are going to be employed over the data from different types of variable is another issue which we would like to understand. So, let us begin this lecture, and in this lecture we are going to talk about the arithmetic mean. We will see that where this arithmetic mean can be used, how it can be employed in the R software, and how the values can be interpreted. So, let us begin this lecture and try to understand the arithmetic mean. So, we all know that whenever we are trying to study any of the statistical aspect, then we need to define a proper statistical tool to measure it quantitatively. So, first we try to understand how we can measure the central tendency of the data. Right. We know that whenever a process is going on, there are one or more than one variables on which we try to create the data. So, the data set may have one or more than one variable, and every variable has many observations. This observation can be fixed, or there can be a continuous flow of the observation. For example, nowadays if you try to see the data generating process, if we are getting the data on that how many people are using the Google Maps or how many people are visiting a particular shopping website, then you can see every second people are entering and leaving. So, this data will always be changing and there will be a continuous flow of the data, right. And if we want to understand that what is the central tendency of the data, or we want to know what is the value around which the average of the value is concentrated, or the value around which the data is concentrated, right, then in case if we try to know this information from the individual observation, then it is very difficult to handle each of the observation and to dig out the information from every observation and to combine them together. So, one simple option is that we can be interested in getting the summary of information hidden inside the data. Right. Instead of getting the information from individual observations, we can get the data on the summarized observations, or that data can be in the form of a consolidated information. So, how to get it done? For example, if you try to say, if I try to suppose know that how many people visit the shopping website every day to buy electronics. Right. So, in case if I try to say on say day 1 this many number, day 2 this many number, day 3 this many number, then it will become very confusing to understand for a layman. But if you try to say, okay, suppose there are 100 people on an average who are visiting the website to buy the electronic item, then it will give a consolidated information, or the information in a summarized form which can be easily understood. Similarly, if a garment trader wants to store some woolen garment before the arrival of the winter season, then the trader might be interested in knowing that how many woolen garments should be ordered before the arrival of the winter. So, now if you say that, okay, this is based on the past data, okay, 1 year somebody used 1020 woolen garments, 1 year somebody used 1070 woolen garments and so on, but this will not actually help. Based on that, he has to order one number. So, he or she would be interested in knowing that, okay, what was the average number of woolen garments that were sold in the last couple of years, and based on that the trader can order the woolen garment for the next year. Right. Similarly, if the tourism department of a hill station wants to know that how many tourists are expected to visit the hill station in the next 2 months, based on that they are going to make different type of arrangement, right. So, now if they try to collect the data from the past, and then if they come to know that, okay, that in these many days these many tourists arrived in the hill station, it may not really help them. But if they get a summarized observation, suppose if they say that, okay, last year during these 2 months there were 5,000 tourists which came to the hill station. So, 5,000 means it was not 5,000 is this tourists every day, but on some day it was 4,500, some day it was 5,500, some day it was 4,500 again, sometimes it was 4,800 and so on. But the average value is close to 5,000. Right. So, one can say that, okay, in the next 2 months, it's every day they expect that about 5,000 tourists are going to visit that particular hill station. Similarly, if somebody wants to know for a particular examination that who is qualifying this examination more oftenly, girls or boys. So if they come to only the numbers, if they try to give the numbers, that may not be very helpful, but if they try to give us that on an average that these many boys have passed the examination and these many girls have passed the examination, that will give us a broader idea that who is passing the examination more. Right. So these are, and then there can be different situations where this arithmetic mean or the central tendency is of the data is required to be known. Right. Now let me try to take one more example. Suppose we get the day's temperature of last year in the two cities, Lucknow and Srinagar, in the month of May for 5 days. So you know that during the month of May, the Lucknow is located in Uttar Pradesh, which is quite actually hot, and Srinagar is located in the Jammu and Kashmir, where the weather is going to be quite cold. And suppose we get the data like this in Lucknow on those 5 days, the temperatures were 35 degrees centigrade, 37 degrees centigrade, 36 degrees centigrade, 40 and 38 degrees centigrade. And similarly in Srinagar, the temperatures were 20, 18, 17, 22 and 23 degrees centigrade. Now, there can be different types of information which are needed and can be drawn from this set of observation. Suppose if somebody wants to know that what type of clothing is needed to visit these two cities in the month of May. So now you can see here by looking at the data of the Lucknow, this shows that okay, the value is concentrated around say about 36, 37 degrees, and the values in the Srinagar, they are concentrated around 20, 21 degrees centigrade. So this means the weather in the Lucknow will be quite hot and weather in Srinagar will be quite cold. So now based on this information, the whether is hot or cold, the tourists can carry the required clothing. So these are different types of averages based on which the policy decisions are taken and the policies are formulated. And this is actually the natural human tendency to compile the information in terms of the average. If somebody asks you that okay, how much time do you take from your home to your college every day, you will say okay, it's about 20 minutes. What do you mean by it's about 20 minutes? It means that you are trying to collect the values of the last couple of days about the time which you have taken, and then you are trying to average them. But when you are trying to average them, you are not understanding what exactly are you doing. Right. There are certain calculations which are happening behind the mind or happening inside the mind, and then you are telling this information. For example, sometimes we say that the average marks in a subject in a class are 60%, and based on that we try to understand that how is the class doing in studies. And sometimes you see that the doctor says, okay, take this medicine after every 6 hours. Why? Because the medicine tablet can control the fever for about 6 hours. But do you really think that is it going to be really 6 hours, or how this value 6 hours has arrived? So, which means that this experiment was conducted on couple of patients. They were given the medicine, and the time up to which the temperature or the body fever remain in control was measured. Sometimes it was 7 hours, sometimes 6 hours, sometimes 5 hours, sometimes 5.5 hours and so on. And then an average was taken out of those values, which came out to be 6. So the doctor knows that on an average, one tablet can control the body temperature up to 6 hours, and based on that they try to take a proper decision. Right. So such statistical concept refer to the average or the central tendency of the data. So now with this different example, I have tried to explain you that why this concept of average is needed and why do we want to study this thing here. So there are various measures to study the central tendency of the data. This can be arithmetic mean, geometric mean, harmonic mean, median, quantile, mode, etc. So we will try to study them one by one. Right. Now, whenever the data comes to us, as I told you that one of the approach is to first make a graphical presentation. So suppose if you try to look at this data set, which I have here two data set. One is presented in red color and another in green color, and I have created a scatter plot. Now you know what is a scatter plot, and this scatter plot looks like this, that the data is concentrated in this region and the data is concentrated here in this region. What do we infer from this data? If I say that the data in the red colored dot is concentrated somewhere around this, yeah, there can be a variation in your discussion and might say this argument, you can say the data is concentrated here or here, that is okay. But then you will see that you won't say that the data is concentrated somewhere here, right, at this place. This is wrong. So you can see that the data is concentrated somewhere in this region. So this is the value which is the mean of these observations. And similarly, if you try to look at the green dots, you can see that here the data is concentrated somewhere in this region. So this value is the mean of the observation of the second data sets. Let us call them here as a mean 1 and mean 2. And suppose this is your here x axis on which we have plotted the data, right. Suppose I can say that these are the BAM marks of, say, male students, and these are the marks of female students, right. Now you know that how you can make group plots, right. From the same data set you can classify them into male and female, and then you can plot such a scatter diagram. So if you try to see by looking at the scatter diagram, it is giving us an idea that around what value the data is concentrated, and this is referred to as the mean value. Now how to find out this mean value? This is the issue which we are now going to discuss. So when we talk about the arithmetic mean, then suppose if we have the observation x1, x2, xn, what does this actually mean? Suppose I take 20 students and if I ask their ages. So the first student tells my age is 20 years. So this is my here x1. Because here I am indicating that the ages are being indicated by a random variable x. Similarly, the second student says my age is 22 years. So this means here it is x2, the second observation on x variable. You can recall that earlier we had discussed that we usually denote by capital X the random variable and by lower, say, alphabets, say small x, their values. So similarly, you have, say, collected here 20 observations, say the 20th observation is 23 years and so on, right. So whenever I am writing here the observations are x1, x2, xn, these mean these are some lower values, and particularly I will be writing these values in lower case, right. So now the arithmetic mean of these observation x1, x2, xn, that is defined as, say, 1 upon n, I goes from 1 to n, summation xi. So if you try to see, this is the sum of all the observations divided by the total number of observation n, right. N is here the total number of observation. And this value is usually denoted by x bar. That is the common mean symbol for arithmetic mean. And in R software, mean, MEAN, inside the parenthesis the data vector x, is the command which provides the value of the arithmetic mean of the data in the data vector x. And in case some values are not available and they are missing in x, then in that case we have to use the option na.rm is equal to true. Recall that we had discussed that if some data set is missing, then that data set is indicated by capital N, capital A, and A. And then in that case, we use the command, say, mean for the data vector x, in which some values are indicated by NA, and we try to inform NARM, that means remove NA values, and then compute the function, right. So this mean inside the parenthesis data vector x with na.rm is equal to true will remove the missing values from the data vector, and it will find out the arithmetic mean of the remaining values. Right. Okay. For example, let me try to take here an example to explain you how we are going to do it. So Yeah, so here I have recorded the time taken by 20 participants to complete a race. This time is recorded in seconds, like a 32 second, 35 second, 45 seconds and so on. And this data is stored in a data vector here, time, like this. Now, if you look at this data, what do you here get the information? It is very unclear, right? In case if I say, okay, the first participant took 32 seconds, second take 35 seconds, third take 45 seconds, fourth take 83 seconds, fifth take 74 seconds and so on, what do you really get an idea about the information? It is very difficult. So, we try to find out here the arithmetic mean using the command mean, MEAN, of time, and this value comes out to be here 56, right? So, this means that on an average I can say that the participants took approximately 56 seconds in completing the race. And this is here the screenshot of the same observation of the same data. Now, in the same example, I want to illustrate that if you are going to miss some data, then how are you going to handle it? Suppose two data points in the same data set gets missed, and you can see here these two data sets which are here 32 and 35. I am writing here, say here NA and NA. NA means they are missing. So, now there will be 18 data points in the data set, and I try to store it in the data vector where I will use all the numerical values, and for the missing values I will write here NA, and then I am just giving this data vector a name time.NA, so that you can understand that this is the time data vector where some missing values are indicated by NA. So, this is my here data vector. Now, in case if you try to operate the command mean over this time.NA, then you will get here only NA. And in case if you use here mean time.NA, NA.RM is equal to true, then you will get here the values here 58.5, right. In case if you use here the time.NA mean, and then you use here NA.RM is equal to false, which is the default actually. In this case, if you try to see in the first case, I am not using any NA.RM, but NA.RM is equal to false is the default option here. Then this value will come out to be here NA. So, you can see here this is here the screenshot of the same operation. So, what is happening in the case of this first case or in the third case, it is trying to take here all the values, say NA plus NA plus all the values divided by here 20, that is why it is giving here the value 20. And in the case of here, say this here second case, it is trying to find out the mean of 18 available values, right. Something like I goes from 1 to 18, xi divided by 18, right. So, that is what is happening here in this case. So, this is exactly what I want to show you here before we move further, that when I am trying to take here the complete observation, then it is computing x bar is equal to 1 upon 20, I goes from 1 to 20 xi, and when I am removing the two missing values and I am trying to compute the mean of time.NA, then it is actually computing 1 upon 18 summation I goes from 1 to 18 xi, right. So, let me first try to show you these things on the R console, so that you can be confident that these things are working, and yeah, these things are available in the base package, right. So, you can see here this is my here time data vector, and you can find out here mean of here time. So, you can see here this is here 56, and if you try to say here time NA dot RM is equal to here false, you will get here the same value 56, and even if you try to use here the NA.RM is equal to true, even then it will give you the same value. Why? Because you see in this data set there is no missing value, so automatically R is unable to remove any data set, right. And but on the other hand, in case if you try to create this data set where the first two values are here missing, then you will see it will make a difference. You can see here this is your here time.NA, right, two values are missing. Now, if you try to find the mean of this here time.NA, right, then you can see here it is coming out to be here NA. And even if you try to say here that NA, if you use the command here NA.rm is equal to here false, that means please don't remove the missing values and then calculate it, even then it is coming out to be NA. But in case if you try to use it here NA.rm is equal to true, then it will come out to be 58.5, right. And in the same data, if I just want to show you that in the same data set time.na, I remove this NA, right. And if I just save it here as say time, say here 1.na, and if I try to find out here the mean of time 1.na, you can see here this will come out to be the same as 58.5 like as here. So from this I can show you that when we are using this command that na.rm is equal to true, then it is indicating only here the mean of those values which are available, right. Let me try to take here one more example from the data set which you have considered couple of times in the past. It is about the painters data set in the mass library. So you can upload this library using the command this library mass. Then you can see that here there are 5 variables which are composition, drawing, color, expression which are quantitative, and school is variable which is qualitative. So under this thing you can see that the data on this expression is here like this, which you can obtain here. Now if you want to find out the mean value of this expression data, then simply I can use here mean, and then within the parenthesis I can use here painters dollars expression, and it comes out to be 7.66. And so you can see here what I wanted to show you here is that if you have a big data set where there are many variables, and if you want to study only the mean of some values or mean of one particular variable, then you can simply take out that variable by using the command dollar from that data set, and you can operate such a statistical function directly over it. So this was my objective to show you. Let me try to show you whether this really works in the R software or not. So let me try to first load the library mass, and after that I will use here mean. So it will come out to be here like this 7.66. So you can see here finding out the mean is not difficult at all, right. So you can see here up to now I have considered the ungrouped data, right, and here I have shown you how to find out the arithmetic mean. Now I will try to use here the grouped data. You can recall that when we consider the frequency distribution of discrete and or say this attribute and continuous variable, so or discrete variable or say continuous variable, then we had prepared the frequency table in 2 ways, in which in the case of attributes we have simply counted the numbers, whereas in the case of continuous data or even the discrete data also we had converted them into some frequencies using the intervals, right, using the class intervals. So just for your recollection, you can recall that we have created the class intervals based on the range of data. Then we had found out the midpoint of this class interval, and we had found that how many observations are lying in this class interval, and that was indicated by here absolute frequency, say here Nj, and then we had found the relative frequency, say here Fj, as the absolute frequency divided by total number of observations. So for example, F1 is going to be say N1 upon say here N, where N is here the total number of observation, N1 plus N2 plus Nk, if there are K classes. So you can see here these are our K intervals, then M1, M2, Mk, they are the midpoints of this class interval, N1, N2, Nk are the absolute frequencies, and F1, F2, Fk, they are the relative frequency. So obviously as I said, Fi is equal to Ni upon N, and yeah, sum of all relative frequencies will always be equal to 1, right. Now in this case, the arithmetic mean for such a group data is obtained by here say 1 upon n summation I goes from 1 to k ni mi, right. So mi is the mid value and ni is the absolute frequency, and small n is the total number of observations. So this can be written here as say summation I goes from 1 to k fi mi, right. So another equivalent version of such a mean is the weighted arithmetic mean, that it is given by here summation I goes from 1 to k wi mi divided by I goes from 1 to k wi. So where this wi's are actually the weights. So this weighted arithmetic mean is useful in those situations where we want to assign some particular importance in terms of weight to the data. For example, if you try to look at this simple arithmetic mean, which was like x1 plus x2 plus here xn divided by here n. So you can see here that here we are giving equal importance to each and every observation, but when I am trying to make it here something like wx1 plus w2x2 plus here say here wn xn divided by here w1 plus w2 plus here wn, then this becomes the arithmetic mean, which is actually the weighted arithmetic mean, right. So this is how we try to compute the arithmetic mean for the group data. This is what you have to keep in mind. Now we can compute the arithmetic mean of this group data by defining here two data vectors here m and af. So m is here the data vector of the values m1, m2, mk, which are the midpoints of the class interval. And similarly here there is another data vector here which is containing the values n1, n2, nk, which are the absolute frequencies of the class intervals. So this I am denoting here by here say af, absolute frequency. And now I use here the command here weighted dot mean, weighted dot mean, and within parenthesis m comma af, right. And one thing what you have to keep in mind here is that this data vector af in the this weighted dot mean m comma af is denoting the data vector of the absolute frequencies and not the data vector of the relative frequency. This is what you have to keep in mind, right. Don't get confused with the letter here f. It is only indicating af, that is absolute frequencies, and weighted dot mean will automatically compute this quantity here, right. So now let me try to take here the same example which I took earlier, which was earlier for the discrete data. Now I will consider this data as a continuous data. So you can recall if that we have taken the example where the time taken by 20 participants in completing a race is recorded, and the time is recorded in seconds, like a 32 seconds, 35 seconds and so on, and this data is stored in a data vector time, right. Now if you are going to consider this data as a group data, then you know that you need to first prepare a frequency table in which you need to create the class intervals, find out their midpoints, and then find out their absolute frequencies, right, to compute the arithmetic mean. So we have created here the confidence interval like 31 to 40, 41 to 50, 51 to 60, 61 to 70, 71 to 80, 81 to 90, and then we have computed its midpoint like as 31 plus 40 here divided by 2 will be 35.5, and similarly 81 plus 90 divided by 2 will be 85.5. And then I have observed the absolute frequency, and I have written here the absolute frequency that there are 5 values which are lying in the interval 31 to 40. There are 3 values which are lying in the interval of 41 to 50 and so on. But this I did manually, and we had learned, and you can recall actually when we created the frequency distribution table for the continuous data, then we had used this concept like breaks and cut to create the frequency table. And the idea was that when you are trying to use the command table, the table command is used to create the absolute frequency in case of attributes or the qualitative variables, right. And when you are now considering the quantitative variable and you want to create the frequency table by using the command table, then somehow you need to convert this quantitative data into factor data, right. So that is why we have to follow these steps. The first step is to create the class intervals, and the second step will be to compute the absolute frequencies. So we are just going to follow the same steps that we had followed earlier, and to create the frequency distribution in case of continuous data. If you get confused or if you cannot recall, you can go back to that lecture and can have a look before continuing here, right. So you can recall that we had defined a data vector breaks, BREAKS. Now we are trying to create here the confidence intervals of length of width actually 10 at an interval of 10. So I can create here a sequence using the command seq from, say here this is here from 30 to 90 by 10. That means the sequence at an interval of 10 integers. So, breaks will give me this type of value 30, 40, 50, 60, 70, 80, 90. And now I have to use here the command here cut, just like earlier on this data set time. I want to break it using the interval which are of width 10, which we have created by the option here breaks. And then right is equal to false means the right bracket is going to be open bracket. And now I store this data into time dot cut. So, you can see here this time dot cut comes out to be here like this. 30 to 40, 30 to 40, 40 to 50, 80 to 90 and so on. And you can recall that what was the interpretation of these things. Suppose if I say here, if I take here 2 data values or say 3 data values, you can see here in this data set, this is first data value is 32, then 35 and then 45. So, these intervals are indicating that this is the value 32 is lying in this interval, the value 35 is lying in this interval and the value 48 is lying in this interval. So, this is what it is indicating, and that I explained you in that lecture very clearly, right. So, now I try to create the frequency distribution of this data time dot cut. So, I try to use here the command table over this time dot cut, and you can see here this is here the frequency table, that in the interval 30 to 40 there are 5 observations, 40 to 50 there are 3 observations and so on. So, it is essentially trying to count that how many times 30 to 40 has appeared in this data set, right. You can see here 30 to 40 4 times, right. And so, this is what it is trying to show you here. So, you can see here this is, I can just use another color, 30 to 41, 30 to 42, 30 to 43, 30 to 44 and 30 to 45. So, this is indicated here by this here 5, right. So, similarly other data set has also been extracted or the counted. Now, what we have to do, this is the frequency table. I want only here the frequencies. So, how to extract only the frequencies from this frequency table data? For that you can recall that earlier we have used the command as dot numeric, right, and inside the parenthesis we have given the frequency table data. So, I use here as dot numeric, and then this data which is here table of time dot cut, this comes here, and you can see here whatsoever here are these frequencies, they have come here in the data vector here f. You can see here this is the same frequencies which are here like this, right, 533, 522. So, this is how I have extracted the frequencies. This is the only job which I have done up to now. Now, after this you have to create the data vector of the midpoints, and then you have to use here this here f, and then you have to use here the command weighted dot mean, WEIGSTED weighted dot MEAN say MF. So, it will give you here the value here 56, right. So, first let me try to show you that how these values are going to be obtained. So, first let me try to create here this sequence of here breaks. So, you can see here this is here the time data set which is already here. Now, I create here this here breaks. So, you can see here this is here the same data set, and now I try to use here this cut command and create a new data vector here time dot cut. So, you can see here time dot cut comes over here like this, and now I try to create here the table of this data in the time dot cut. So, you can see here it is here like this, right. And in case if you try to just save this data as say here AF, which was the absolute frequency we had used. So, that will be as dot numeric, and then inside the parenthesis table of here time dot cut, right. So, you can see here now this will give you here the absolute frequencies AF, and then I can use here the command here weighted dot mean. But for weighted dot mean we also need the mid values, say here m. So, let me try to copy this values here so that I can save some time. So, this is your here like this, and after that if you use here the command here weighted dot mean, but now I will have to use here the command here AF. So, I can use here weighted dot mean, say here m comma AF, right. You can see here this is coming out to be here 15, right. So, you can see here it is not difficult, but now I want to show you here something very different. So, you can see here we had converted this data time into, and we considered it as a continuous data, and we converted into the form of a frequency table, and then we found this weighted mean. But now in case if I try to find out here simply the mean of a time without converting it into the frequency distribution for the continuous data, you can see here this value is again coming out to be this almost the same, or in case this is exactly the same as 56. So weighted mean and mean here in this case they are coming out to be the same. So now I would try to show you here something very interesting, that from the conceptual point of view we have understood that when we want to find out the arithmetic mean of ungrouped data, then it is found by mean command, and when we are trying to find out the arithmetic mean of grouped data, then it is found by using the command weighted.mean. Right. In the context of this data science, usually the data size is going to be very, very large, and you will see that most of the data is continuous or even this discrete also, right. So if you try to convert the continuous data in the format of a frequency distribution using this process which I have shown you, there may not be much a difference in the values of mean and weighted.mean, right. The values are be very, very close. For example, in this example which I took, the mean of the time when we are considering as a group data or ungrouped data, it is coming out to be exactly the same, right. And in case if your data size is actually quite large, quite huge, then you will see that the difference between the two processes is coming out to be almost the same. So when you are trying to consider the random variation in the data, then a small difference in the values of the means obtained by either mean or weighted.mean will not make much difference. For example, if I say that this year's the total income of a person is going to be, say here 54 lakhs 534 rupees or 56 lakhs 531 rupees. It will not make much difference actually practically. Mathematically there is a difference. So what I am trying to say that when we are dealing the data in the data science, when the data is particularly quite huge, either this is discrete or continuous, then we can safely use the mean command in the R software, and which will not make much difference. But definitely if you want to be more precise, that if you want to consider the data only in the form of a group data, then you have to follow this process. But anyway, my job was to tell you both the approaches, and I have done my job. So it is you who is going to decide that under what type of data which tool has to be used. You are the best judge, right? So now I stop in this lecture. I have tried my best to give you an idea about the concept of central tendency of the data. Now it is your job to understand this concept. The best thing is that I will say again, try to generate a data which has very less variation, that the values are very close to each other, and then try to find out its arithmetic mean. Then try to increase some deviations in the values, that the values are quite far away, and then try to compute its mean, and then try to see what's really happening, right? In case if the deviation on the both sides of the central value is almost the same, then the values will still be concentrated in the midpoint, nearly in the midpoint, and then try to increase the data set and can see how this mean function or this concept of arithmetic mean is going to give you the information which is contained inside the data set. And similarly, try to take some bigger data set which are available on different websites, and try to see how you can understand about the mean value or the central tendency or the average value of the data. You need not to look into the entire big data set, but just one value will give you a good piece of information about the entire set of data. So you try to practice it, and I will see you in the next lecture with next measure of central tendency. Till then, goodbye.